Welcome to this video, where we explore two powerful features for optimizing and managing data in Azure SQL with Django: row compression and temporal tables. If you are building a Django application that relies on SQL Server, these tools can help you improve performance, save storage, and manage data history seamlessly. By the end of this tutorial, you will understand how to set up row compression and temporal tables in your Django project, and you will see how these features can be tested and verified using Azure Data Studio or Visual Studio Code with the MS SQL extension. Before we begin, make sure you have a Django project set up. Ideally, this should be the same project from our previous video, so you are already familiar with the basics. You'll also need Azure Data Studio or Visual Studio Code with MS SQL extension installed. These tools will help us inspect and manage our database, ensuring that the features we implement are properly configured and functional. To support row compression in our Azure SQL database, we will create a custom database backend. This involves defining a new module named DB inside our Django project directory, test Azure SQL, where the settings.py file is located. Inside this module, we will add a base.py file with the following code. This custom backend modifies the behavior of Django schema editor to enable row compression for all tables created in the database. Here's what the code does. Database schema editor class. It inherits from the existing MS SQL database schema editor class and overrides the SQL create table attribute to include an additional SQL statement that applies row compression. The alter table command rebuilds all partitions in the table with the data compression equals row, optimizing storage and performance. Database wrapper class. It inherits from the MS SQL database wrapper class, sets the schema editor class attribute to our custom database schema editor class, ensuring that all database operations using this wrapper will utilize the row compression behavior. This setup ensures that every new table created through Django's ORM will automatically have a row compression applied, streamlining the optimization process. This code can be easily modified to support other types of row compression or features during table creation. For example, you could replace data compression row with data compression page, or add additional SQL options like partitioning strategies, indexing, or encryption configurations. This flexibility allows you to tailor the backend to your specific database optimization needs. In the next step, we need to update the databases setting in our Django project. Specifically, we change the engine to point to our custom backend by setting it to test Azure SQL DB. This ensures that Django uses our modified backend for database operations. We won't test the row compression setup just yet. We'll verify it later once we have our temporal tables configured and operational. Temporal tables are a powerful feature in Azure SQL that allow you to track changes to your data over time automatically. By enabling system versioning on a table, you create a historical log of all changes made to the data, including when each change occurred. This can be incredibly useful for auditing, compliance, or simply understanding how your data evolves. With temporal tables, SQL Server manages two tables behind the scenes: the main table, which stores the current state of the data, a history table, which contains previous versions of the data, complete with timestamps indicating when each version was active. This feature eliminates the need to manually manage historical data and provides seamless querying capabilities to retrieve the state of the data at any point in time. In the next steps, we will set up the infrastructure to create and manage temporal tables in Django, ensuring a clean and efficient implementation. To manage temporal table functionality, we will create a new module named Temporal Tables in our project directory. Inside this module, we will add a models.py file with the following code. This module provides utility managers for working with temporal tables in Django. Temporal Annotation Manager. This manager is designed to work with history models, annotates the current query set with sysStartTime and sysEndTime, which are special system columns managed by Azure SQL Server for temporal tables. It uses row SQL and cast to dynamically include these columns as part of the query set. Temporal Module Manager. It inherits from Temporal Annotation Manager and extends it with additional methods for interacting with both the current and historical versions of the data. Get from history. Retrieves a specific historical version of a model instance. Filter history. Filters historical records based on specified criteria. Filter union query set. combines the current records and their historical counterparts into a single unified query set. Temporal Annotation Manager will be used with history models, while Temporal Model Manager is intended for default models to enable seamless integration of temporal functionality. In the upcoming steps, we'll demonstrate how to use both in practice. To further enhance our temporal tables functionality, we will add a DB migrations PY file inside the temporal tables module. This file will contain raw SQL commands for converting a standard table into a temporal table and removing temporal functionality. Here is the content of the file. Convert to temporal table. Adds two new columns, says start time and says end time. These columns track the start and end of each record's validity period. The generated always as row start and generated always as row end clauses indicate that these columns are managed by the system. Default constraints ensure that every record has valid timestamps upon insertion or update. The period for system time clause establishes these columns as the period columns for the table, enables system versioning on the table, linking it to a history table specified by history table name. The data consistency check option ensures that data integrity is maintained. Remove temporal table disables system versioning for the table, drops the history table if it exists to free up space, removes the period for system time and associated constraints, deletes the sysstart time and sysend time columns, effectively reverting the table to a standard configuration. These SQL scripts will be utilized in Django migrations to convert a table to a temporal table and revert it back if necessary. It's important to note that the migration enabling temporal tables should come after the default Django migration that creates the table. In the next steps, we will create a Django app to demonstrate temporal tables in action and incorporate these SQL commands into the migration process. We have now created a new Django app named Temporal Tables Usage and added it to the installed apps in our Django settings. This app will demonstrate how to use temporal tables with the models in Django. Here is the content of the models PY file for this app. Common data. An abstract model containing a single data field. This field is shared between data and data history models. Being an abstract model, common data is not created as a table in the database, but serves as a base class for other models. Data represents the main table where current data is stored. It uses Temporal Model Manager, a custom manager from the Temporal Tables module, and this manager allows interaction with both the current and historical data, providing methods to query, filter, and combine records. Data history represents the historical data for the data model, uses Temporal Annotation Manager to annotate query sets with system timestamps, the start time and the time, for better insight into historical data. Marked as managed false, meaning Django will not manage this table, e.g. it won't create or alter it. Instead, this table corresponds to the history table managed by Azure SQL's temporal table feature. The DB table attribute explicitly defines the name of the database table or data history. By using specific model managers, these models gain powerful querying capabilities tailored for temporal table use cases. This setup prepares us to integrate raw SQL migrations for enabling and managing temporal tables in subsequent steps. Now let's dive into the migrations for setting up our temporal tables. First, we will use Django's make migrations command to auto-generate the migration for our models. This command will look at our models and generate the basic SQL schema changes necessary to create the tables for data and data history. This step will create an initial migration file that sets up the tables based on the model definitions. However, this migration will not convert our tables into temporal tables yet. That's where our custom SQL comes in. Next, we need to create an empty migration so we can use to insert our custom SQL. This is done with the empty flag. This will create a new empty migration file, and the Temporal Tables Usage app will now add our custom SQL logic to convert our tables into temporal tables. Now let's modify the empty migration file to include the raw SQL commands that will convert the data table into a temporal table and set up the history table. Here's the migration code that does this. Let's break this down. Original table name and history table name. These are the names of the current table and the historical table we are working with. We define this here to keep the code clean and avoid hard coding table names multiple times. Dependencies. This defines the dependency of this migration on the initial migration that was auto-generated earlier. This ensures that Django knows this migration should run after the initial migration that sets up the models. Operations. In this list, we specify the actions that will be performed during this migration. Migrations run SQL. This is a special operation that allows us to run a raw SQL during the migration. The first argument is a SQL command to be executed to convert the data table into a temporal table. The second argument, reverse SQL, specifies the SQL that will be executed if we roll back the migration. In our case, it will remove the temporal table setup and restores the table to its original form. The convert to temporal table and remove temporal table are predefined SQL templates or from the temporal tables DB migrations module. These templates will format the SQL command with the appropriate table name. After updating the migration file, we will use the migrate command to apply the changes to the database. This will set up the temporal table configuration and allow us to start using temporal features in our data and data history tables. This command will execute all the pending migrations, including our custom migration, and convert the data table into a temporal table with the appropriate history tracking. Once the migration is complete, you can check the Azure SQL database in Azure Data Studio to verify that the table is now a system versioned table. At this point, we have successfully set up a custom migration to convert a normal table into a temporal one. With this in place, we are now ready to start using temporal features like querying historical data. In the next steps, we will explore how to check if the row compression is enabled on the table. Now that we have set up our temporal table, let's demonstrate how to check if row compression is enabled on our temporal tables usage data table. Row compression is a key optimization in SQL Server that can save storage space by compressing rows. We can check if this feature is enabled by using the following SQL query. Sys tables. This system view contains information about all the tables in the current database. We join it with the other views to get specific details about compression. Indexes. This view contains information about all indexes, which is important because compression can be applied to individual indexes in SQL Server. Partitions. This view holds partition information for tables and indexes, including the compression type used on each partition. Data compression description. This column gives the description of the compression type used on the partition. If compression is enabled, it will show a value like row or page. If it's not enabled, it will return none. Workflows. We are specifically looking at the temporal tables usage data table, filtering on the table name and ensuring that the index is a valid one, e.g. type is more than 0. Order by. We order the results by table name and index name to make the output easy to read. The results should show a list of indexes associated with the temporal tables usage data table, along with the compression type for each index. In this tutorial, we covered setting up temporal tables in Django with the SQL Server database. Here's a brief recap. Project setup: we created a new Django app and defined models for managing current and historical data. Temporal tables module: we created managers and custom SQL migrations to enable temporal table functionality. Django migrations: we auto-generated migrations and used custom SQL to convert the data table into a temporal table with an associated history table. Verifying setup: we confirmed the temporal table setup by inspecting the database in Azure Data Studio. Row compression: we checked if row compression was enabled using custom SQL queries. Next steps: with the temporal table set up, you can query historical data, track changes, and optimize storage. This process allows you to manage time-based data efficiently using SQL Server's temporal table features in Django. If you found this tutorial helpful, don't forget to like, comment, and check out our dev website if you are interested in Django project development. See you in the next video.